Hello and welcome. In this video, we are going to talk about rate master equation. We start with very simple systems and continue our considerations for more and more complicated systems. So, as the very first example, let's consider a closed system, which is also a mixed system. Therefore, we can only describe its state with a density matrix, which is living in H1 Hilbert space. So we have this system, a multi-level system, or as the simplest case, you can consider a two-level system. This system has a Hamiltonian, which we show with H0. This system has this Hamiltonian which quantizes this system into some energy levels, like this, E1, E2, up to En, or maybe even more. And each of these states has a population, because we are working in a mixed system which has a density matrix. We are going to actually find some equation for the evolutions of the density matrix, which is, by the way, the only thing we have to describe the state of the system. We can't use a wave function because it's a mixed system. So we have density matrix, right, for a closed system, and we want to describe the dynamics of this density matrix in terms of time. So the well-known relationship for this state is the Liouville equation, which gives this formulation. This is a very simple equation, and if you sandwich the sides of this equation between the eigenvectors or eigenkets of H0, which let's show with M, and considering these M's form an identity matrix, they are a complete set, and therefore this sigma over M's actually forms an identity matrix in the system's Hilbert space. Therefore, by sandwiching them between two M's like this, and after some algebra, we end up with this more scalar representation. This is just a same equation but with a little different mathematical representation. And omega, by the way, is just the energy. This is a very simple case in which we have just a mixed state which is closed, and there is no external perturbation and external interference from the environment, which would be the second Hilbert space. All we have here is the first Hilbert space, which belongs to the system. Now, let us imagine that in the second case, our system is no longer a closed system, and therefore is an open system, and it is obviously still a mixed system, which again needs to be represented by a density matrix. And this time we have an environment which is defined in another Hilbert space. So we have the first Hilbert space, for example here, in which system is defined with an intrinsic Hamiltonian of H0. And then we have the second Hilbert space, which is the environment, or let's call it reservoir. The reservoir and environment are quite the same. There is very subtle differences, which in its own literature is important. But let us, for now, to be more technical, let's let's consider our environment as a reservoir. A reservoir basically is a subset to the environment. All right, we're not going to go into the details in this video. So the intrinsic Hamiltonian of H in the H2 for a reservoir would be, let's show that with, I don't know, maybe H2, but that is not very important for us at this moment. And then the adjacency of this system and the environment or reservoir gives out a third Hamiltonian, which is very, very important, and it's defined in the both Hilbert space, and we show that with interaction Hamiltonian. This belongs to both Hilbert spaces. All right. So what we have here is the same very system, which is and the same very dynamics to the first state, which was the system itself only, but with some addition. So I'm going to have this equation again, all right, but with some addition, which I'm just going to write it with an R, and again this time a row. Okay, I'm not going to open the and dissect the mathematical structure of R at this moment, and we are going to consider only the main or the diagonal terms in which m is equal to m prime. All right, then according to the previous equation here, what we are left with is just this part, because m and m prime, when they are equal, this omega, which is just the difference of energy between m prime and m, would be 0, because it would be the same energy of m prime, because m is equal to m prime, right? It would be 0, and therefore we are left with this part only. So we would have only rho m t equal to a matrix R, and again rho itself, a parameter called WMN. And WNM is the transition rate from n to m, so from this to this. And what does it mean? It's actually the probability per unit of time that the transition happens between from n to m. And if you're still wondering what are n and m, they are just the energy levels of our system. So it could be 1, 2, and somewhere between them n, and somewhere between them n. Okay. And by the way, we have a counterpart for this one, which would be W nm, which would be the transition rate from m to n, right? So I'm not going to repeat all the above, just a repetition sign here. So we have the dynamics of our the state of our system, the density matrix of our system. It says that the dynamics of the state mm is equal to the changes that happen at that very moment in terms of flying actually electrons or whatsoever the system is from a state n to m. Okay, but that's not all, because at the same time there are some systems or subsystems which are flying from m to other n's. And remember, this sigma here says that m is not going to be equal to m, because they are not going to therefore they're not going to be the same. never at all, right? So the changes here are indeed the arrivals to M minus the departures from M. But is that enough? No, it is not, because this is not just the transition rate, but also the number of people who are applying for this transition, which is this number of people is displayed with these two population matrix or density matrix. So for example, these are the arrivals from N to M. So it does matter that how populated is N. There might be a very good tendency to flight to M, but there might be at the same time not many electrons there. So the number of electrons there is also a parameter. So this should also be multiplied by W. And the same thing about here. So the number of people who are living in M and are going to leave M to other N's, which are supported by the sigma other N's instead of M itself. The number of these people who are already living in M matters, and this important thing is actually displayed mathematically with this density matrix here. So here is the quite well known in this literature equation for the changes in population of states. We're going to stop this video at this moment, but maybe as a final point, I'm going to write very briefly what these are. So this is the instantaneous temporal changes of rho mm at time t. Okay, what is this one? I mean the whole term here shows is, again, I mean the whole term. Okay, the whole term here represents the gain in M, okay, from all other N's. And finally this term, whole of this term here, shows the loss from M. And consider we are remember we are talking about M state after all. So loss from M to all other. All other means this sigma here. All other N's. Okay, so that's it, guys. This is the equation, and I hope that you got a good intuition to this rate or master equation. We're going to continue this discussion in the next videos.